Hi guys, welcome to another chemical engineering tutorial brought to you by the ChemEng student. In this lesson we're going to take a look at ternary liquid-liquid extraction methods. Now I'll also remind you that this is the October competition, so we have a question at the end of the video for you to enter to win £500 every month for a full year. So the first question is, what is a ternary liquid-liquid extraction method? Because previously we've considered how to apply the McCabe-Thiele method for a binary liquid-liquid extraction method, and this tends to be used for distillation columns. Now, a typical schematic that you would use for the McCabe-Thiele method is shown here. Now we use similar nomenclature and similar properties for the ternary liquid-liquid extraction, but the question is, if we use this method, would this still work for a triple system rather than just a binary system? Well, unfortunately the answer here is no, and the reason is simply due to the fact that this is two-dimensional. Because in terms of what we actually have is we have the mole fraction of the lighter component within the liquid phase and the mole fraction of the lighter component in the vapor phase. So here we only consider the XY plot of one of the compounds in the respective states. The other is the reciprocal for the plot. So here we consider the feed, we consider the distillate, and we consider the bottoms. Because if we know that, say for example, this is 50% of the lighter component, we assume that it's 50% of the heavier component as well. Likewise, imagine this was 90% of the lighter component, we would know the reciprocal is 10% the heavy. Now, the construction of the tie lines and the Q lines is pretty much going to be the same thing. So the question is, what is the solution for a ternary liquid-liquid extraction? Then there's generally two ways that we can express this. One applies a right-angled triangle and the other one uses an equilateral triangle. And these tend to look something like this. Now we'll talk about the details as we go through this video, so we'll understand every single variable and then we'll look at a full working example so that it is very clear how you actually apply this type of system. So the first thing that we can notice here is on both sides, now we're going to call, this one is for a specific system. This is for the water and acetone and a TCE, which is the trichloroethene molecule. So here we're going to call the water component A. So what this means is that we will highlight that at component A on both of these graphs, the opposite line indicates a binary mixture between component B and component C. Because at this stage here, we have pure 100% water. And here, there is no water within the system, so we only have two components, i.e. a binary mixture. And it's the same thing here. If this is pure A, then by the time we get to this point, there is no A left. And that's echoed throughout the entire graph. So say that TCE is component B, then that means that the line directly across from it is a binary mixture, or in this case of pure A and C. Likewise, exactly the same thing. And then again, if we look at component C, then the line directly opposite would be a binary mixture of A and B, i.e. there is no C at this point within the system. Likewise, right here. Now this one is slightly more simplified compared to this, but the general principle still stands in that we have this curve here and we have this curve here. So again, the system is pretty much exactly the same, but for this we get a more comprehensive idea of the concentrations. Now, in order to actually read these graphs, I'm going to use the more comprehensive one, but you can apply this to the right angle triangle as well. Now, the interpretation of one of the sides is exactly the same for all three. So how we interpret one of the components is exactly the same for the others as well. So essentially what we do here is as you move parallel from your respective axis, so in terms of your respective component, then in this case the concentration varies by a factor of 10%. So for example, here that we have pure TCE here, therefore when we start to move from point to point, then the concentration begins to vary. So what that means here is that in this case, then for the water system, we have no water at all here. As we move further and further towards the water, our concentration increases by 10%. So that's on this axis. So here, at this point, we have 100% water. As we move on these diagonal lines, because remember it has to match this slope, it moves and gets closer to 0. Now that's echoed throughout. So if we consider the TCE, then at this point here we have 1, so that would be 100%. But as we move away from the TCE, i.e. as we head towards the binary mixture of A and B, then you can see that the concentration decreases by a factor of 10%. So these lines, as we travel away, we decrease by 10%. And then lastly, the same thing with the binary mixture of A and B. So the acetone here is at a concentration of pure acetone, so 100%. But as we move away from acetone, we can see that it gets less and less and less, up until the point where the concentration is 0. So this line here is for acetone, this line here is for TCE, and this line here is for the water. So again, you just need to make sure that your nomenclature is carried out correctly, and that you remember that on this type of graph that we move in increments of 10%. Now the intersection of these lines would provide us with a composition at the given point within the system. So for example, at this point here, then what we would say is that the water is 50%, so we have 50% water. We then, if we read down here, we have 30% in terms of TCE, which means the remaining value would be 20%. So if we do 50% plus 30% plus 20%, we can clearly see that we get 100%. So that's what the makeup of this point would be on both the streams, all 3 streams. Now the regions that we haven't discussed yet essentially represent the nature of the phases. Because inside the curve, so we can express this as inside the curve, so that would be at this point, so this curve here, right? So inside the curve would be in this region. Then what we have here is this is the 2-phase region, i.e. we would have 2 distinctive liquid layers. So kind of like, oil and water, how they would be immiscible with each other. Because TCE, so the trichloroethane, and water are completely immiscible with each other. So they will always form a bilayer, so a 2-phase region. Whereas here, in the outer region, we have a single phase region, i.e. we would have one single layer of liquid. Now, the single phase simply means that rather than having, so here if we draw this on a beaker, so the 2-phase region would be, we have liquid 1 and we have liquid 2. We would see the distinctive layer. But here, what we would have is L1, L2 in the same batch. We wouldn't see this distinctive layer. So that's the difference. Now within the 2-phase region, we can now see we have these lines. Now these are called tie lines, and the tie lines give us information about the equilibrium within the system. So that's all these lines here. Now, there is a special point at this part here, so if you were to follow the lines as we gravitate towards the edge, when these points kind of intersect and converge, where the turning points basically become zero, then this is known as the plate point. So this is where the concentration, the composition of the distillate and the raffinate are exactly the same. Now we've introduced two new terms here, and we'll talk about them in just a second. But essentially what we're saying is that the composition, because remember this denotes equilibrium, that the composition between distillate and raffinate become the same. Now let's take a look at a working example here. So we want to determine the flow rate of the raffinate and the extract of a system that contains trichloroethane, which we're going to denote as T, and this is pure solvent at 150 kilograms a second, to remove acetone, so that's component A, from water, which is component W, which is a feed rate of 100 kilograms per second, and a composition of 45% and 55% respectively. So essentially what we need to do is we need to work out the following. So if we take this as a one-stage system, so it's single stage, we don't have multi-stage. So we have the feed coming in, so that would be the one that contains the water and the acetone. And we have our solvent feed coming in, which is going to be our TCE. Now the raffinate is the top product. So the the extract becomes the bottom product. Now notice that these are in counter current flow, and that's really important so as that we can improve and optimize the rate of mass transfer. It's the same principle for heat transfer. Now what's important to notice here is that these streams are in equilibrium with each other, the feed and the solvent. Now that means that the extract and the raffinate are also in equilibrium with each other. Now this is for single stage. If we had multi-stage, we would just repeat the same process. Now what we need to do here is we need to perform, so using this as a guide, we're going to perform a mass balance on the system. And what we can do is we can make a plot of the compositions. So to start off with, we know that the feed contains 55% water and 45% acetone. So that would be the feed point here. Now we know that the solvent contains pure TCE, i.e. we have no water and we have no acetone. So that's right down in the very bottom corner here. Now that means that we can have the feed stream plus the solvent stream is equal to this point M. Now M is the mixing point of the system, and we'll come on to that in just a second. Now we can determine what M is in regards to flow rate, because that's going to be the total. So that's going to be the flow rate of the feed plus the flow rate of the solvent. So that means that M flow rate is 250 kilograms per second. Now we can connect these points together. So this is like our operating line. Now what we need to determine is the value, so that the composition of the mixing stream, so at M. And the way that we do this is we perform individual balances. So we'll balance the acetone first. So we'll say what is the composition of the acetone in the feed multiplied by the flow rate. Now we don't have any acetone in the solvent stream, so we can just disregard that, so that will disappear. And then we have the composition of acetone in the mixing point. This is the thing that we want, and the flow rate at M. So we can pop everything in, and we work out that at this mixing point, the composition of the acetone is 0.18 or 18%. Now we just repeat the same process, but this time we'll do it on the water. So we know that the water constitutes 55%, so we'll times that by 100, and then we'll divide that 250 by that value. So that tells us that we have 22% water at the mixing point. Then what we can say is that the remaining, so the balance for the trichloroethane, would be 1 minus the summation of the composition of the water plus the composition of the acetone. So that tells us that we have 60% TCE at the mixing point. Now these are the coordinates for the mixing point. So all we need to do is identify whereabouts on the graph these lie. So we can see that our mixing point must lie on this line. So there is going to be an inherent slight error here because we're using a graphical representation. So it's open to interpretation ever so slightly. But so long as it's within a acceptable tolerance. So for example, we know that TCE is 60%. So we would go along, this is 90%, 80%, 70, 60. So we know that it must lie on this line. Now we can clearly see that this is the point that it's going to be. But we can get some confirmation on that because we know that, say for example, the acetone, or we'll go for the water is around 22%. So we go the water here, so it would be 0.9, 0.8, 0.7, 0.6, all the way up to 0.2. Now we can see that it's about here. So if we draw a line all the way down, we can see, I mean it's not going to be straight, but you get the general idea. We can see that it will intersect there. And if we perform the same thing, you can see there is a slight tolerance of error, but we are on the operating line, which means this is our point M. So this is the mixing point, and now we know we do indeed have a two-phase system. Now we need a tie line, and this needs to be drawn from point M. So remember, this is point M. Now our tie lines are these lines here. So we want to be as close, we're very, very close to this line. So this is a fixed given tie line. So we're just below. So what we'll do is we'll match the same gradient and we'll intersect at these points here. And these are the important points because this is the raffinate at this point here, so to the right, and the extract is to the left of the equilibrium line. Now all we need to do from here is we read off what the respective coordinates are for the water, the TCE, and the acetone. That will give us the composition of the raffinate. So if we say that the composition of acetone and the raffinates, that's acetone and R for raffinate, is if we go all the way down here, so remember this is for the acetone, then what we can see is that if we come down to about here, then if we go halfway and along, we can see that that's around the 50% mark at this point on the raffinate. So that's 15% for acetone. Then we could do the same, but this time for the water. So we see if this is pure water, then this is 90% water. So we're between 90 and 80. And it looks like we are just about at 82. So we say about 0.82. Now the remainder is going to be these values added together and 1 minus that. But again, you could do the same thing here, but with the TCE. So you can clearly see that we are on that line and we're smack bang at 3. So we know that there is a slight error here, but we are well within the tolerance. And we would do exactly the same thing, but this time for the extract. So here we would get around 23% for acetone, about 5% for water, and the remainder being about 72% for our TCE. And again, you can just double check that, because TCE here is 100%. And we're here, so we've got to keep the same gradient. So we're about here. So you can see that that's 70%, so that's 72%. All right. So now from here, what we can do is we can construct two equations, and we can do this based on a water balance, and we can do it on a TCE balance. So we do this so that we can determine the raffinate and the extract flow rates. Because if we do a balance on the water, then we know we'll have the composition, so the XWR, so that's the composition of water in the raffinate, plus the composition of the water in the extract, must be equal to the composition of the water at the mixing point. So if we substitute in the values, then we get an equation of 0.82R plus 0.05E must equal 55. Now if we do exactly the same thing in a balance on T, we will substitute in the respective coordinates that we achieved for TCE at both the raffinate and the extract. So we get 0.6 because we had 60% in the mixing point. Total was 250. So we got 150. Now again, you could do this based on, rather than doing M, you could say that R plus E equals F plus S. But we know that F plus S was M. So that's why we used M rather than F and S. Alright, but you could do exactly the same thing and you get the same answer. So now what we can do is we have a set of simultaneous equations. We have two unknowns, two equations. Now we can do this by either elimination or substitution. Here we'll do it by substitution, i.e. we will rearrange one equation and substitute it into the other. Now, just to note that we did interpret the results, so there will be an element of error within the values. So what we'll do is we'll rearrange this equation for R in terms of E. And now what we will then do is we'll take this equation and substitute it in for R in the second equation. So therefore we've replaced R as a function of E. So then all we would do from this point is we would multiply this bracket out. We would then collect the like terms, collect the E's, bring that number across, and that will tell us that our mass flow rate for the extract would be 203.45. We know the total, what comes in comes out, is 250. So we do 250 minus 203.45. So we get a value for the raffinate of 46.75 kilograms a second and 145.97 kilograms per second for the extract. And that's how you would go about solving a ternary liquid-liquid extraction using the triangular coordinate system. And again, this is for a single unit. You can apply the exact same methodology for multi-stage units as well. So now towards our competition. So to win £500 every month for an entire year, this is for our October draw, is all you have to do is give us an example of a ternary azeotropic mixture. So you would need to know what an azeotropic mixture is, and there is only a select few, so be sure to comment your answer of the three components that would make up a ternary azeotropic mixture. Now to enter, simply comment your answer to this video, like and subscribe to the channel, and also make sure that you are subscribed to the Facebook page, as that's where the winner will be announced on the 5th of November. The competition closes on the 31st of October, so make sure that your entries are in before then, and any other videos that are uploaded in October will be entered into the October draw. So that's the end of this lesson. Thanks for watching. Hopefully this was helpful in understanding the concept of ternary liquid-liquid extraction methods for single units. If you liked this video, please like and subscribe to the channel. It really helps us reach as many chemical engineering students as possible. Thank you for your time, and we hope to see you in another video.